It's reviewing a lot of what we've already done in Chapter 4. So the examples that I have on here, we're going to go through these as a group just because I want to make sure you understand the different ways you could work through a problem. I want you to understand how to work through it. And it's just a lot that we need to discuss more as a group while we're reviewing, but also tying it into what's new in this chapter or in this lesson. So it's all on quadratic inequalities. The first part is just covering what the first example is having us do, and that's graphing a quadratic inequality that is in two variables, so you have an x and a y. So graphing inequalities, if you think back to graphing linear inequalities with lines, when you graphed those, you first graphed a line, but you had to pay attention to whether it would be solid or dashed. So the only difference here is you're graphing a parabola, but you want to make sure you know whether it should be solid or dashed. And then we tested a point to see what side to shade. Here, we're still going to test a point to then see, are we shading inside of our parabola or are we shading outside of it? So the overall process is the same. The difference is that you have a parabola and not a line like we had before. So this is really going to be reviewing what we first did in this chapter, graphing a parabola. So if you need that review before you start reviewing tomorrow, this will be a review of that. One thing I do want to review, how do you know whether or not you have a solid or a dashed line, or in this case a parabola? How do you know, or I'll ask this, when is it going to be solid versus dashed? When it has the or equal to. So if you have less than or equal to, greater than or equal to, it'll be solid. If it's just less than or greater than, it's going to be dashed. So mainly you just need to pay attention to if it's dashed, because normally when you're just drawing it in, you draw it in solid. So just pay attention if it should be dashed before you draw it in. But we're just going to look at example 1. So it says graph y is greater than x squared minus 3x plus 2. So the first step, graph the parabola. So you're graphing the related function, which is y equals x squared minus 3x plus 2. And this is thinking ahead, but when we graph this, is it going to be solid or dashed for this inequality? Dashed. So thinking ahead before you actually draw your parabola in, when you get to that point, make sure it's dashed. So here we have a function in standard form, ax squared plus bx plus c. This is a review for how to graph. How do you graph this? What do you find first? We can find the axis of symmetry. How do you find that? Yes, opposite of b over 2a. So again, that's a formula you'll be given, but you have to know that's what it's used for. So back up to our equation here. What is our a value? 1, b is -3, and then c, we don't need it for that formula, but it's 2 for when we do need it. So opposite of b would be +3. 2 times a is 2 times 1, that's 2. And 3 halves is the same as 1.5. So x equals 1.5. So I can draw in a dashed vertical line through the x value 1.5. And after the axis of symmetry, what can we find? Vertex is a point. X value is from your AOS, so x coordinate is 1.5. Substitute that into your function to get your y coordinate. So we have 1.5 squared minus 3 times 1.5 plus 2. So -0.25 is the y coordinate. So it's just barely below the x-axis there. All right, and then again, because this is just graphing, I do want you to have 5 points. So what's another point we can find? The y-intercept. And what is that? 0, 2, or just if you had 2, if I asked you for the y-intercept, if you just had 2, that's fine. So I can plot a point at 0, 2, and then if I reflect that over the line of symmetry, what other point do we know? 3, 2. Okay, so the table, actually setting up a table is optional. You don't have to do it. I'm just going to do it to organize what we have. Okay, so we need 2 other points. So what else could we substitute in? -1. It doesn't matter. Sometimes, and the reason I asked is, I don't know why, but sometimes when the vertex is a decimal, students think they need to then plug decimals in. You don't need to. I can plug in -1 because I don't have a point for that x value yet. So make sure though, when you plug in -1, -1 squared is going to be +1, and then minus 3 times -1 plus 2. This will give you a y value of +6. So -1, 6. And then to get our 5th point, we don't have to plug anything in. We can just reflect it over to what point would we have? 4, 6 as well. And then remember, before you draw your parabola in, it should be dashed. Or if you already drew it in and it's solid, make a note that it should be dashed. Okay, so that's the first step. Just like before we had lines, now we have parabolas. So now to determine where to shade, we're either shading in the parabola or everything outside of it. You test a point. You can always use 0, 0 unless your parabola goes through it. So because our parabola does not go through 0, 0, we could use 0, 0. And make sure you're going back to the original inequality. So I'm going to replace the y and then both x's with 0. So I would have 0 is greater than, and then when I replace the x's with 0, those terms are just going to be 0. So I just have +2, so +2. And is that true or false? It's false. So look at where 0, 0 is. Where am I going to shade? In the parabola or out? Inside. Because 0, 0 is outside, but it's not a solution. So I shade the other part, which is going to be inside. So make sure also you're drawing your parabolas actually through your coordinate plane so you have a clear inside part and outside part. You have a boundary there. Okay, so that's really connecting to a process you've done before. Are there questions before we move along? Okay. So the rest of these examples are then solving quadratic inequalities that have one variable. So if you even skip down just to look at example 2, so they're going to look like this. So you don't have a y, so you're not graphing the inequality to shade like we did before. You're just trying to solve this inequality. It looks like the equations that we've been solving, but now it's an inequality. Your answer will be an inequality. So there's 2 methods you can use to solve quadratic inequalities, and the first method we're going to talk about is solving by graphing. And we are going to be going through 2 examples of this, but, and I realize this is probably really hard to see on my screen. It'll be a little easier to see if you look at your sheet. But this kind of explains the form your solutions will be in and why. So I'm going to talk about this and then reference it when we go through examples 2 and 3. So you're either going to have, for your quadratic inequality, it's going to be in one of these 2 forms. Either it's ax squared plus bx plus c is less than 0, and this could be less than or equal to, or it's going to be greater than 0, or greater than or equal to. And then beneath each of those is explaining what that means on a graph. So the ax squared plus bx plus c, that would be referencing the y values of a graph. If you had plugged an x value into that expression, it's giving you a y value. So it's saying to solve it by graphing, you would graph that related equation, y equals ax squared plus bx plus c. And then because the inequality is saying that y is less than 0, the y values are less than 0 when the graph is below the x-axis. So you're identifying the x values for which the graph lies below the x-axis. So looking at the two graphs that are next to that explanation, they give you an example of a graph that's opening up and opening down because the solution set will look different. So for the first graph that's opening up, they're giving you two x-intercepts, x sub 1, x sub 2, and what I did last hour, I'm going to do it this hour. I'm just going to assign an actual number to those just to hopefully make more sense to you. I'm just going to say x sub 1 is the value 2, and then x sub 2 is the value 6. So rather than looking at all of these different x's, maybe seeing a number will help make more sense. But say those are your x-intercepts. So on the graph, if I'm identifying the part of the graph that's below the x-axis, for the graph that opens up, it would be that u part of the graph, the part of the graph that's in between the two x-intercepts. So because it's the part of the graph that's between the two x-intercepts, and it does list below the form of the solution set, but this solution then would be x values that are between 2 and 6. So x values between the values of your x-intercepts. Those x values will have corresponding y values that are less than 0, is what that says. So then when the parabola opens down, the solution set looks different because you have a different part of your graph that's below the x-axis. So I'm going to do the same thing. I'm going to call the x-intercept x1. I'm just going to say that's 2. And the x-intercept x sub 2, I'm going to say that's 6. But the part of the graph that's below the x-axis when it opens down are the two ends of the graph. And therefore your solution set is written differently because the left part of your graph, this part, would be the part of the graph for x values that are to the left of 2. So this would be x values that are less than 2, because it's to the left. And then the other part would be anything to the right of 6, so it would be x values that are greater than 6. So your solution set would be x is less than 2 or x is greater than 6. Okay, so again, if you go back to the original inequality, if it's less than 0, you're looking at what part of the graph is below the x-axis, and then the solution set is written differently depending on what part of your graph it is. If it's the part in between the x-intercepts or the part of the graph that's outside of your x-intercepts. So a big thing is you need to know what your x-intercepts are. That's huge in solving an inequality. So then if it's greater than 0, it's just the opposite. So now this would be you're identifying x values for which your graph lies above the x-axis, because now your y values would be greater than 0 is what the inequality says. So I'm not going to go through in as much detail because it's basically this. The solution sets would look the same, but it's what's above. So the first one, what's above the x-axis would be the two ends of your graph, so your solution set would match what we had talked about here. And then for the second graph, when it opens down, the part of your graph that's above is the part that's in between, so that would match what the solution set looked like in that first one. So those solution sets would be set up the same way. So like I said, we're going through examples of these, but that's kind of an overview when we get to actually writing our solution, what it's going to look like. So your solution is going to look like one of these two compound inequalities when we're done. Okay, so I'm going to move this as long as we're good. Look at example 2. So the problem, they're just going to look like this. It says solve negative x squared plus 3x plus 10 is less than or equal to 0, and it says solve by graphing. So that's important because we are going to also go through an algebraic method to do this. So to solve by graphing, now this does not mean that you need to find the axis of symmetry, find the vertex, plot 5 points, make this really detailed graph. You don't need to do that. You can, but you don't need to. Here's what I need you to do when you have a problem like this. What you first want to do is find your roots, which again, the roots are the x-intercepts on the graph. Because if you look, like I said, if you look at what we just talked about, you need to know what the x-intercepts are. So find those first. Now the x-intercepts, I'm relating vocabulary. We've talked about the x-intercepts are the roots, which are the solutions to the related equation. So I can find the roots without graphing. I can find the roots by solving the equation negative x squared plus 3x plus 10 equals 0. So if I solve that equation, that'll give me the roots, which are the x-intercepts. So this is more review from this chapter on how to solve this. We've gone through a lot of different methods now on how to solve quadratic equations. So what's one method we could use to solve that? Just want to talk about the methods that we've used. What? The x method, the factoring. Factoring is one method. Completing the square. And there's one other one. The formula. The diamond is the factoring. There's the quadratic formula as well. So factoring, completing the square, quadratic formula, in all honesty, whenever you solve a quadratic, whether it's in this chapter, if you don't have to use a certain method and you get to choose one, either in this chapter or later on, you're probably either going to factor or you're going to use quadratic formula most often. But completing the square would also work. Factoring, if it works, factoring does not always work, but if it does work, it's usually quicker than using the quadratic formula. So I at least want to see if we can factor this. And before we do, I'm just trying to point out some helpful things for when you're working through problems on your own. Factoring is easiest if your a value is 1. And right now my a value is -1, but I can easily make the a value +1 if I divide everything by -1. And I can do that as long as I do it to both sides. So I'm first going to divide everything on both sides by -1. That's just going to make factoring easier if it's 1. So then I would have a positive x squared minus 3x minus 10 equals, and then 0 divided by -1 is still 0. So I still have 0 on that side. But then factoring is making the diamond, making the x, however you refer to it, as the setup. So in our trinomial, what would we be multiplying to? And then we're adding to -3. Are there two numbers that work? 5 and 2, which one's negative? The 5. So add to -3. And this is why factoring is easiest if your a value is 1. Because if a is 1, I can go straight to my factors using these two numbers. It's x minus 5 times x plus 2. So if your a value is anything else, that's where you have to rewrite it and group, which you still could do in this case, but this is kind of the shortcut for it. So once it's factored and equal to 0, then how do you solve this? Yes. Set each equal to 0. This is reviewing a lot, but it's good because you need to know it for Tuesday's test anyway. So set each factor equal to 0, solve for x. So the first one, you'd add 5, so x would equal 5. Or second one, subtract 2, so x is equal to -2. Okay, so if the problem just said to solve this equation, these are the answers. However, the problem wants to solve the inequality, so these are part of our answer, but we're not done. These are now the solutions of the equation, so they are the roots, which means on a graph they're the x-intercept. So I'm just going to plot a point on the x-axis at each of these numbers, -2 and 5. And then the only other thing I need to know in order to draw a graph in is whether or not my parabola opens up or down. Because I need to know, am I going to have a parabola, it goes through these points, but does it open up or does it open down? Because that affects my solution. So looking at the equation or the inequality, how do you know if a parabola opens up or down, Allie? Yes, it'd have a maximum because it opens down. Yep. So since A is -1, it's going to have a maximum, it opens down. So I don't care in this problem what the vertex is because it has nothing to do with my answer. I just care what the x-intercepts are and what direction the parabola opens so that I can draw it in. It's not an accurate graph, but it doesn't need to be for this problem. This allows me to figure out what my solution to my inequality is. So now looking back at the inequality, I have less than or equal to 0. So on my graph, am I looking above or below the x-axis? Below the x-axis. It's less than. So I am looking at the two ends of my graph. And I already know what my x-intercepts are. They're -2 and they're 5. And I will say this as well, if you have the or equal to in the original inequality, the or equal to should be in your answer as well. So here's my solution. I have x values then. This part of the graph would be for x values to the left of -2, so x values less than or equal to -2. Or this part of the graph is x values to the right of 5, so x values greater than or equal to 5. So the -2 and 5 are part of your answer, but you need to know then what the compound inequality is, and that you can get from the graph. Is it the two ends, or is it the in-between x-intercepts portion? Okay, there's a lot of review, a lot of understanding that goes with that. Questions on 2. We're going to go through another one of these because it works out a little differently in a couple different ways. So looking at example 3. Now when an inequality is given this way, I don't want you to see this and then when you get to the graph think because the symbol is less than or equal to that you're supposed to look below. If you flipped this around, that means you also have to flip the sign around. So if I flipped this around, it would be -2x squared minus 6x plus 1 is greater than or equal to 0. So in the end, when we have our graph, because it's greater than, we're going to be looking above the x-axis. So try to have the 0 on the right side of the inequality. Switch it around if you need to. That would be my recommendation. Okay, otherwise we go through the same process with this one. So what I want to do first is find where my x-intercepts are. Find the roots. And I can do that by solving the related equation. So -2x squared minus 6x plus 1 equals 0. And because we solved the last one by factoring, I realized the a value isn't 1. I could divide everything by -2, but then because of this 1, I'm going to have a fraction. So before, dividing by -1 was fine. Here, dividing everything by -2 might just make it more messy because then I'm going to have a fraction. So I'm going to leave it. But if I set up the diamonds for this trinomial, what would we be multiplying to? negative 2, so we'd have to multiply the negative 2 and 1, and then we're adding to negative 6. Okay, and I see some no's. We can't do that. To multiply to negative 2, it's either 1 and negative 2 or negative 1 and positive 2. Neither one of those are going to add to negative 6. So I've said before, factoring doesn't always work. Factoring does not work here. That doesn't mean we can't solve it. We just can't solve it by factoring. So we have to use one of our other methods, either completing the square or quadratic formula. And like I said, probably for the most part, your go-to is going to be the quadratic formula if factoring doesn't work. So I'm just going to rewrite in this space, because I don't have it on that board, but x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. That'll be given, so make sure that you know how to use it and that you can identify it, because I did have on the homework quiz yesterday on some of them in all classes, when you were solving using the quadratic formula, it was part of the formulas I gave you, and some people were not using this. So make sure that you know or can identify what the quadratic formula is when you're given the list of formulas. So in this equation, our a value is negative 2, b is negative 6, c is 1. So we have x equals the opposite of b, so positive 6, plus or minus the square root of b squared, so that would be negative 6 squared. I'm just going to write 36 right away. Minus 4 times a is negative 2 times c is 1. That's all over 2 times a is negative 2. And also, because we want to graph the x-intercepts, when you're doing this type of problem, you don't have to leave your answers as exact. You can get a decimal so that you're actually able to graph it to know where it should be. Because sometimes looking at the exact form, if you see, 6 plus the square root of 20 over negative 4, what value is that? So you do want the decimal for these. So we'd have 6 plus or minus the square root of 44, thank you. And then all divided by 2 times negative 2 is negative 4. So this is where I'm saying don't worry about trying to simplify this. Just get your decimals, because you're going to have to plot them on your graph. So this does have 2 solutions. One of them is x equals 6 plus the square root of 44 divided by negative 4. And make sure when you're calculating to get a decimal that you add 6 plus the square root of 44, hit enter, and then divide by negative 4. So that's approximately negative 3.16 if I round it to 2 decimal places. And then the other would be 6 minus the square root of 44 divided by negative 4. And again, evaluate the top of the fraction before you divide by negative 4, and that would be a positive 0.16. So these are your 2 x-intercepts. And then we just need to graph a parabola through them that either opens up or down. Is this parabola going to open up or down? Down. So I just need to sketch it in. It doesn't need to be accurate in terms of where the vertex is, because it doesn't matter to get our solution. So then, since I identified we're greater than or equal to 0, so we're looking above the x-axis, now the part of our graph that's above is the part that's in between the x-intercepts. And you have your x-intercepts, the decimals already. So to write this, you just want to make sure you have the smaller one, the negative 3.16 first, and then the larger one. So it would be written this way, that x is in between negative 3.16 and positive 0.16. So negative 3.16 is less than or equal to x, which is less than or equal to 0.16. Okay, so between the two examples, one was looking below the x-axis, one was looking above, one we had to factor, one we used a different method, and then the solutions, you know, your solutions are going to look like one of the two types. So find your x-intercepts, determine whether your parabola opens up or down to sketch it in, and then identify which part of the graph your solutions are in. Questions on the graphing method for solving an inequality. Okay, because there's one last example, but this one is solved algebraically. And again, it's just an alternative method if you didn't want to sketch the graph. But the very first step is the exact same. So you're still starting out, you have an inequality. I should say before we do step one, you do want with your inequality one side to be 0. So I'm going to rewrite this. I'm going to subtract 2. So x squared plus x minus 2 is less than or equal to 0. But you do want for your first step to still find your roots. So you're still finding the solutions to the related equation. So we have the equation x squared plus x minus 2 equals 0. Solve that equation first. Bless you. So let's see if we can factor this one to solve it. Because our a value is 1 also, so the factoring would be easier. So we're multiplying to -2 and adding to 1. Are there two numbers that work? -1 and 2. Yes, because you want to add to a positive 1. So you want the -1 and the positive 2. So then it would be x minus 1 times x plus 2. Since your a value is 1, we can go straight to the factored form and then set each factor equal to 0. So x minus 1 equals 0, or x plus 2 equals 0, meaning x is going to equal 1, or x equals -2. Okay, so that first step is the same between both methods. Here's where we differ. So before we then determined does it open up or down on a graph, and we graphed it to find the solutions. Steps 2 and 3, we're going to do kind of as one. Step 2 is to draw a number line, and you might want to, depending on how you want to work through it, you might want to draw it so you have enough space. And you plot the two solutions that you just got on the number line. So just make sure the smaller one is on the left of the number line. So I have -2, and then I have +1. And then notice that this divides your number line into 3 intervals. So I'm just going to draw kind of some boundaries between them. So we have 3 intervals. We have to the left of -2, in between the two numbers, and then to the right of +1. So then the algebraic part is to test a value from each interval to see if it satisfies the original inequality. So I'm just going to rewrite so I don't have to have this so low on the screen. Our original inequality was this: x squared plus x is less than or equal to 2. So when you test a value, for example, if we're going to be to the left of -2, pick any x value that's smaller than -2. So somebody pick a value. -3. It can be any number as long as it's less than -2. Plug that in to your original inequality. So I would have -3 squared plus -3, and I want to know, is that less than or equal to 2? So -3 squared is 9, 9 plus -3 is 6. Okay, that's false. What that means is that x values that are smaller than -2 are not part of the solution. So my solution does not contain this interval. Okay, then I move on to the next one. Go on to the middle. What's a number between -2 and 1? 0. So I have 0 squared plus 0. That would just be 0 is less than or equal to 2. That is true. So I do have solutions in this interval. So I'm going to come back to that. I just want to test the last interval quick. I need a number bigger than 1. 2. So then 2 squared plus 2 is less than or equal to 2. That would be 4 plus 2 is 6. And that's not less than or equal to 2. That's false. So that does not contain our solution. So your solution, all of your solutions of x, now 0 is just one of them, but they lie in between these numbers. So my solution is all x values that are between -1 and 2. And again, because my original included the or equal to, I included in my answer. So my answer would be written this way. X values between -2 and 1. So -2 is less than or equal to x is less than or equal to 1. Well, typically it's either going to be in between or both of the outside intervals will be true. So it's either the middle one is true or the outer ones are true, but they would both be true. Okay, so I do have, for the practice for this, some of it is graphing. I don't have the actual problems written on a sheet of paper, but I have grids for you to do the graphs on a sheet. So we do have some time. I'll pull up the textbook if you want to